Good afternoon, everyone. So I'm a PhD candidate at UCL Institute for Sustainable Resources, and together with my PhD supervisor, Dr. Matthew Winning, we've been working on developing a macroeconomic analysis with regard to freshwater uses. And namely today I'm going to be talking about projections of irrigation water requirements under different socio-economic development pathways. Now, I think we've been talking a lot today about irrigation and why is it important. The connection between freshwater withdrawals and crops is pretty apparent. Today we withdraw about 10% of total renewable water resources. That's a global average. Obviously, it has the huge discrepancies in between the different regions of the world. Agriculture is by far the largest user, so we take out 70% of whatever we withdraw goes into agriculture. Now, the global food systems rely highly on irrigated production because it boosts yields. So we have 40% of global crop output coming from irrigated land. And considering that agricultural output is expected to grow by, in this case, 60% according to the FAO experts by 2050, the question is, what are the implications of this expansion of crop production over withdrawals, and what are the implications for sustainability in the way fresh water is being used around the globe? Okay, so this research is exactly about exploring the various socioeconomic pathways and their implications over irrigation water requirements. To do this is a global analysis, so we've been using a global computable general equilibrium model, the RESCU model, which comprises 20 regions, and then it's disaggregated from a crop perspective. We have 8 different crop types, with each one being divided into the rain-fed and irrigated varieties. And then another addition, a feature of this model, is that irrigation water is being treated as a distinct factor of production. And okay, so besides the socioeconomic aspects, which translate into GDP growth and population changes, we've also embedded what is expected to happen with productivity of land. So we've taken data from the IFPRI impact model with regard to the inherent yield changes. So whatever we expect under normal conditions, so no climate change, how would productivity of land would be expected to change up to 2050. And this is differentiated for each crop class and for each variety of the two, the rain-fed and irrigated varieties. Once we derive the irrigation requirements using the RESCU model, we put that in relation to the total renewable water resources within each of the 20 regions in the model. And we use this pressure indicator, which is the irrigation withdrawals to availability, yet another indicator for water stress, but this is tightly related to agriculture. And then we've added the stress threshold just to mark whenever a region enters a zone of irrigation, of stress coming from irrigation withdrawals. In terms of the scenarios we've been exploring, we used 3 out of the 5 now widely used in the climate change literature socio-economic pathways. We have the SSP1, which is coined as the sustainability scenario, SSP2 the middle of the road, and SSP5, which is the conventional development pathway. I'm not going to talk a lot about what CGE models are. I'm going to refer to what are the effects we've been trying to capture in this model, and why was it an opportunity to use a CGE model in the first place. So we have the two, hope this works. The two main drivers. So one is the socioeconomic income and population changes, and then the technological change drivers for irrigation withdrawals or irrigation requirements. The socioeconomic one mainly drives a scale effect. So basically you have a growing population, we have more income, there's going to be a boost in demand for crops, and that's going to have implications over the use of factors of production, and we might expect an expansion of irrigation water uses. At the same time, we also need to bear in mind that the growth in demand in one region of the world is going to maybe translate into additional pressure into other regions, other producing regions. And we've talked about today about the virtual water aspect, which might be a solution for the water challenged regions to supply their water, their crop demand. Now, another important effect is the substitution effect, because, as I mentioned, we've implemented differentiated yield improvements for each crop class, for each growing variety, which then maybe will translate into, maybe in 2015, to a different production mix. So let's say if irrigated land is more productive than rain-fed land, and obviously there's going to be a transition from rain-fed production to irrigated production, which is obviously going to have impacts over irrigation water requirements. So this is the substitution effect, which might lead to a bit of, which together with the scale effect might lead to different outcomes than we would expect necessarily. So in terms of results, the first step is to this is sort of a step where we validate the model results. So this how is crop output or crop production is going to grow in the 2004-2050 time frame. And indeed the scale effect actually prevails, right? So we have SSP2, which is the middle of the row, which delivers an 83% crop output growth. But then the higher economic growth, especially for developing regions, SSP1 and SSP5, they produce higher overall crop production. And at the same time, we also see the substitution effect taking place as irrigated production grows more than rain-fed. This is as a whole. And then at the regional level, we have a certain degree of variability. Not all regions grow in the same way. Now, from a crop type perspective, these are the 8 crop classes we've been using. The scale effect is pretty consistent, as we've seen before. So in order of growth magnitude, we still have this SSP1, SSP2, SSP1, and SSP5 in terms of how much each crop class actually expands. But at the same time, not all crop classes grow in the same way. And then here we have rice, which grows the least because it has the lowest yield improvement as opposed to the other crop classes. Now, returning to irrigation water, we've obtained a 8.5 to 11% increase from 2004 levels to 2050. And this is this is far lower than what we've obtained in the previous slide, where on irrigated production we've obtained a doubling of production. And this is because basically the world moves towards crops that are less water intensive. So each crop class has a different water intensity, and that's why we don't obtain the same growth level. At the regional level, we do obtain high increases in withdrawals in Africa, because that's a high growth region. But also water-challenged, water-stressed regions such as India, Central Asia, Northern Africa, they all obtain an increase in withdrawals. An interesting case here is China, that decreases its requirements for irrigation water, and that's mainly because rain-fed land has better yield improvements. Now, when we put this in the irrigation requirements in relation to renewable resources available for each region, we basically see that the situation does not become any better. Water-challenged regions either maintain their current levels. We have here South Asia, which is composed of Pakistan and Afghanistan, that maintain their current stress, but we have important increases in irrigation requirements in Northern Africa, Middle East, India, and then we have Central Asia, which enters the club of water-stressed regions as defined by our IWA indicator. So here we have the heat map that shows that this strip of land spanning from northern Africa to India is becoming darker, and the prospects for a sustainable use of freshwater resources are deteriorating up to 2050. As conclusions, the socio-economic development leads to an overall increase in water requirements, so higher growth scenarios lead to further increases in withdrawals. So the scale effect prevails here. This is going to be especially a problem for water-challenged regions, and hence this hints at the SDGs. We need to make more efforts into improving water use productivity. This is especially addressed in Target 6.4 in the SDGs. At the same time, we need, as Thomas Hertel was also referring to, productivity as an important factor in regards to irrigation requirements. We have here yield improvements that have a reducing effect over dependency on irrigation water, and that's something that there's also huge uncertainty with regards to how much land yield can improve over time. Now, for us, in terms of modeling efforts, this is, like I mentioned, a no climate change scenario, what you've seen so far. So basically, we need to further consider climate change impacts over growing conditions, and at the same time, we're also planning to look at the evolution of other freshwater uses, because energy, for instance, energy systems are high withdrawers of water. That needs to be factored in at a certain point to have a complete picture of how is water stress going to evolve in the next 50 years or so. So that was me. Thank you so much for your attention.
Well, thanks a lot, Victor. And well, yet another fascinating piece, and thanks also for introducing these innovative modifications to CGE modeling. Quite interesting. Question, remark, statement here. So, yep, there is one question there from a lady there.
Thank you very much. I have no special question, but we didn't understand. You showed a lot of the diagrams, but the letters in the diagrams we cannot read. So
I
anyway,
do apologize.
Next time, please, a big letter, yeah?
Yeah, sure.
Thank you.
Thank you.
Hi, sorry if I missed this at the beginning of the talk, maybe you already explained it, but how do you actually calculate the irrigation water requirements? So how much the crop actually needs?
Well, the data is taken from the global crop water model, which is a global model which takes into account harvested areas and the different water intensities of quite a few crop classes.
So, as in the very first talk today, with like large-scale hydrological models, there's obviously heaps of uncertainty. I was just wondering, have you considered any of that uncertainty? Is that something you've been looking at, and if so, how are you managing that?
Well, we've tried to partially address the uncertainty, the wide range of uncertainties by taking 3 SSPs into account. So, from a socio-economic development, we wanted to explore several income and population growth pathways, and then obviously we need to include other uncertainties in the model, such as climate change, which is in itself has all sorts of variables that we need to address as being uncertain. Yeah.
All right, thank you. Thank you, Victor.